Evening. Now second part, 11 sum. Prove by method of induction. First one, log of x raised to n to the base a equal to n log x to the base a, x greater than 0, small n belongs to capital N. So we begin with, right down. Let Pn denote the statement log x raised to n to the base a, valid base, is n log x to the base a. Okay. Now for n equal to 1, just a minute. What is LHS? Log of x raised to 1 to the base a, that is log x to the base a. And what about right hand side? 1 into log x to the base a, that is simply log x to the base a. So LHS equal to RHS, that is P of 1 is true. Now second step, let P of k be true for k belonging to set of natural numbers. That is log x raised to k to the base a is k log x to the base a. First one. Now we prove that P of k plus 1 is true. That is log of x raised to k plus 1 to the base a is k plus 1 into log x to the base a. LHS. What is log of x raised to k plus 1? Laws of indices. X raised to k into x. Now log mn, or here log ab, is log a plus log b. That is logarithm of product is sum of the logarithms. Okay. So k log x to the base a plus log x to the base a. Or before that, I'm sorry, a log of x raised to k to the base a plus log x to the base a. But note that from 1, see the cursor. What is log of x raised to k to the base a? K log x to the base a. Okay. And therefore, here we say that from 1. Okay. Yes. So it is k log x to the base a plus log x to the base a. Okay. So if you take log x to the base a common, you get k plus 1. This is nothing but right hand side. Therefore, P of k plus 1 is true. Step 4, from above and, please do not write in this fashion. This stands for and by the principle of mathematical induction. P of n is true for all small n belonging to capital N. That is log x raised to n to the base a is n into log x to the base a, where n is a natural number. Now, third part, let me explain, please, but do write the solution after the lecture. Third part, prove by method of induction, 5 raised to 2n minus 2 raised to 2n is divisible by 3 for all natural values of n. Let Pn denote the given result. Step 1, for n equal to 1, we get 5 square minus 2 square, that is 25 minus 4 equal to 21, which is divisible by 3. So P of 1 is true. See, some students say, sir, we cannot complete the solution. If you write just first 2 steps, now writing 2 steps is not at all difficult. You will get at least 1 or 2 marks if this sum is asked for 4 marks, right? But I'm sure you'll be able to complete the solution. Second step, let us assume that for some natural value of k, pk is true. That is 5 raised to 2k minus 2 raised to 2k is divisible by 3. Means if you divide this by 3, you get a natural number, say m. So if you cross multiply, you get 5 raised to 2k minus 2 raised to 2k equal to 3m. So 5 raised to 2k is 2 raised to 2k plus 3m, number 1. Now, step 3. To prove that P of k plus 1 is true, that is to prove 5 raised to, please do not write 2k plus 1. Previously it was 2k. Now it will be 2 times in bracket k plus 1 minus 2 raised to 2 into in bracket k plus 1 is divisible by 3. Now we consider this part separately. See the cursor. So 5 raised to 2 into k plus 1 minus 2 raised to 2 into k plus 1 is 5 raised to 2k plus 2 minus 2 raised to 2k plus 2, which is 5 raised to 2k into 5 square, that is 25, minus 2 raised to 2k into 2 square, which is nothing but 4. But note that 5 raised to 2k is what? 2 raised to 2k plus 3m multiplied by 5 square, which is 25. Reason is given from 1. And after that, open the bracket. So you get this 25 into 2 raised to 2k plus 75m minus 4 into 2 raised to 2k. 25 minus 4 is 21. At this stage, you can say that this is divisible by 3, hence the result. Or you may take 3 common, right? So that this is nothing but this one. So this divided by 3 is 7 into 2 raised to 2k plus 25m, which is a natural number. This means p of k plus 1 is true. Before that, you have to say this is divisible by 3. So in the fourth step, you have to say from all the above steps and by the principle of mathematical induction, p of n is true for all small n belonging to capital N. For convenience, we have denoted this by Pn. Some students may denote this differently. So it is better that we say that is 5 raised to 2n minus 2 raised to 2n is divisible by 3 for all natural values of n.
Sum number 13. If the middle term in the expansion of x plus b by x whole bracket raised to 6 is 160, find b.
Actually, index is 6. So there are how many? 6 plus 1. That is 7 terms in the expansion. So fourth term is the middle term. Now T4 is T3 plus 1. Why to write T4 as T3 plus 1? Because we have formula for TR plus 1. It is NCR x raised to n minus r into in a plus b raised to n. What is TR plus 1? NCR a raised to n minus r into b raised to r. Here n equal to 6. First term is x, second is b upon x. But that is given to be 160. So we write an equation. Now 6c3 is 6 factorial upon 3 factorial into 3 factorial. Comes out to be 20. Into x cube into b cube upon x cube is 160. So b cube equal to 8. So what is b? B is nothing but 2. Sum number 15. If the constant term in the expansion of x cube plus k upon x raised to 8, if the constant term in the expansion of x cube plus k upon x raised to 8 raised to 11 is 1320, find k. Let tr plus 1 be the constant term in the expansion. We know that in the expansion of a plus b raised to n, what is tr plus 1? NCR a raised to n minus r b raised to r. So a is x cube, b is k upon x raised to 8, n is 11. So this is general term. Okay. Now for this term to be a constant term, see some students they equate this with 0. That is wrong. Why? Because we need a single term in x. So use laws of indices to get x raised to 33 minus 3r. Here x raised to minus 8r. I hope you are getting this. So single term in x is x raised to 33 minus 3r minus 8r. That is 33 minus 11. Now for this term to be a constant term, index of x must be 0. So that gives me 33 minus 11r equal to 0. That is r equal to 3. So which is the constant term? 11c3 into k cube. It is given to be 1320. Now 11c3 comes out to be 165. So 165 k cube is 1320. Solve this equation to get k cube equal to 8. So k is nothing but 2. Sum number 16. This is an important type. We haven't covered this. Show that there is no term containing x raised to 6 in the expansion of x square minus 3 upon x raised to 11. One method is just go on expanding, write all the 12 terms and then say that, see, there is no term in x raised to 6. But why to write those terms? So we use shortcut method, which is allowed in exam. You can use this. So general term. What is the general term in the expansion? This is the general term. Use laws of indices to get a single term. Now, I have used R. What is R? Many students say R is natural number. See, the first term is T1. So for that R has to be 0. And that is why I have written that R is a whole number. Okay. So for a term in x raised to 6, index must be 6. Equate index with 6. You will notice that 22 minus 3R equal to 6 gives R equal to 16 upon 3, which is not a whole number. Why this is so? Because there is no term in x raised to 6. Right? This is the proof. Actually, sum number 17 is again similar. I'll write solution in short. First, complete this. 17 show that there is no constant term in the expansion of 2x minus x square upon 4 raised to 9. As usual, I have obtained general term. Please check this. TR plus 1 9CR 2x raised to 9 minus R into minus x square by 4 raised to R. Collect constant term, constant part 9CR minus 1 by 4 raised to R 2 raised to 9 minus R. Then x raised to 9 minus R. And x square, rather x raised to 2R. You may ask, what about this negative sign? I have already written minus 1 by 4 raised to R. So, as per laws of indices, it is x raised to 9 minus R plus 2R. So, 9 plus R. Now, for a constant term, index of x must be 0. Equate 9 plus R with 0. That gives me R equal to minus 9, which is absurd, as R has to be a whole number. It can be 0, 1, 2, 3, 4, etc. So the conclusion is there is no constant term in the expansion of 2x minus x square upon 4 raised to 9. 22nd, find the approximate value of 1 upon 4.08 up to 4 places of decimals. Now 1 upon 4.08 means what? 4.08 raised to minus 1. That is 4 plus 0.08 raised to minus 1. Within bracket, take 4 common. So 4 raised to minus 1, that is 1 upon 4. Now this is 1 plus 0.02 raised to minus 1. What is 1 plus x raised to n? 1 plus nx. N means minus 1. X is this. Plus n into n minus 1 by 2 factorial x square. This is not required. But if you want, you can write this. Now simplify. So 1 upon 4 into 1 minus 0.02 plus 0.0004. So 1 by 4 into 0.9804 comes out to be 0.2451. If you consider next term also, then I'm sure using rounding off rule, you will get the same answer. 24th is good one. A plus bx into 1 minus x raised to 6 is 3 minus 20x plus cx square plus dot dot dot. Then find the values of ABC. Now, a plus bx into 1 minus x raised to 6. Expand this using binomial theorem. Then find out binomial coefficients. Actually, I don't think we are required to find all, but they have obtained all the 7 terms in the expansion. Okay. Basically, see, constant term, a term in x and term in x square. Only these terms are required. So even you need not find term in x cube, x raised to 4 and so on. Okay. Or at least do not simplify. Now, if you open the bracket, you get constant term as what? A into 1, that is A. Then, which is term in x? You have to be careful. A into minus 6x is in x. Bx into 1 is also in x. So if x is taken common, minus 6a plus b. See, which is a term in x square. See, a into 15x square and bx into minus 6x is again a term in x square. So if x square is taken common, 15a minus 6b. Now it is given that this is 3 minus 20x plus cx square and so on. So from 1 and 2, we can have A equal to 3, simple. Okay, then minus 6a plus b has to be minus 20. But as a is obtained, b comes out to be minus 2. Then coefficient of x square, which is 15 minus 15a minus 6b, is nothing but c. As we have obtained the values, we can find the value of c also. Okay, so a equal to 3, b equal to minus 2, and c equal to 57. The third term of 1 plus x raised to n is 36x square. Find fifth term. Now I have written general term in the expansion. So what is third term? T3 is T2 plus 1 NC2 1 raised to n minus 2x square given to be 36x square. Means NC2 is 36. Now what is NC2? N factorial upon n minus 2 factorial into 2 factorial. I omitted one step. Factorial of greater is factorial of smaller, gets cancelled. Into, go on adding 1 unless you get greater. So n minus 1 into n upon this 2 equal to 36, 72. LHS is, you are expected to write this. Like LHS, we express RHS also as product of two consecutive natural numbers. So that gives me n equal to 9. What is asked? Fifth term means T4 plus 1. Now n is 9. So 9C4, actually it is 1 raised to, that is why I haven't written that, into x raised to 4. 9C4 is 126. So 126 x raised to 4. That is fifth term. 26th, suppose 1 plus kx raised to n is 1 minus 12x plus 60x square. Find and so on. Find k and n. Now what is 1 plus kx raised to n? I hope you remember the expansion. 1 plus nx means n into kx plus n into n minus 1 by 2 factorial. 1 raised to, but that is 1. That is why I have directly written square of kx. That is k square x square. Compare with this. So 1 is 1 obviously. Nk is minus 12. And this is k square. I'm sorry. This into k square is nothing but 60. Because coefficient of x square is 60. Now, k square is kk. So nk into nk minus k, because you have to multiply both the terms by k. But nk is minus 12. We have to write the reason for this. So minus 12 into minus 12 minus k is 120. That gives me minus 12 minus k equal to minus 10. So k is minus 2. Put k equal to minus 2. That gives me n equal to 6. So these are the values. Okay. So we have completed this topic. But before I end the lecture, let me tell you about Pascal's triangle. For that, we are going to see the video on the same.
To the binomial theorem, we need to learn an important and interesting concept. We need to know something called the Pascal's triangle. Wondering what it is? Come, let's see. The Pascal's triangle is a triangle made up of numbers. Is that it? No, of course there's more to it. Let's see what a Pascal's triangle actually looks like. It looks something like this. Do you observe any pattern here? Have a close look. In the Pascal's triangle, each number is the sum of the two numbers directly above it. Yes, notice that 2 is the sum of 1 and 1. This 3 is the sum of 1 and 2. And this 3 is the sum of 2 and 1. 21 is the sum of 6 and 15, and so on. What else do we notice? We also see that the starting and the ending numbers are always 1 in each row. Yes, all the numbers on the extreme left and all the numbers on the extreme right are all 1. In the Pascal's triangle, the rows are numbered starting from 0. This is the 0th row, this is the first one, then the second one, and so on. The third row is 1, 3, 3, 1. The fifth row is 1, 5, 10, 10, 5, 1, and so on. And you may be wondering why we need such a triangle. What do we even do with it? Don't worry, you'll get to know that soon. First, let me tell you some real interesting facts about the Pascal's triangle. Take a look here at these two diagonals on either side. What are they? Oh yes, they are the set of natural numbers. Awesome, isn't it? Can you find more patterns here? Check out these two diagonals. What could these possibly be? The numbers are 1, 3, 6, 10, 15 and so on. For each number, let's imagine the same number of circles. Let's arrange them like this. What do you see? We see that for each number, we can form equilateral triangles. 3 can be arranged like this, 6 can be arranged like this, and so on. Such a set of numbers is called as a set of triangular numbers. Interesting, right? Now let me ask you the same question again. Do you notice any other pattern? It could be anything. Give it a shot. I want you to observe each row. Let's see what happens when we add up the numbers in each row of the Pascal's triangle. Try adding up the numbers in the second row. Adding up these numbers gives us 4. Now can you try adding the numbers in the third and the fourth row individually? What numbers do you get? Yes, we get 8 and 16. Do you see a pattern here? 4, 8, 16 and so on. 4 can be written as 2 squared, 8 is 2 cubed, 16 is 2 raised to 4 and so on. How can we generalize this pattern? Yes, the sum of each row can be represented as a 2 raised to the number of the row. You can check it out for any row. Take the 7th row for instance. We will get the sum as 128, which is nothing but 2 raised to 7. So many patterns, right? But you may be wondering, how will we use this Pascal's triangle in the binomial theorem? Let's see how. Can you tell me the formula of a plus b the whole squared? Yes, it's a squared plus 2ab plus b squared. Can you tell me what the power of the binomial here is? You're right, it's 2. This power is also called the index of the binomial. Now, before we proceed further, we need to know what binomial coefficients are. Binomial coefficients are the coefficients of each term in the expansion of the binomial. Can you tell me what the binomial coefficients here are? Yes, they are 1, 2 and 1. Now let's go back and see the Pascal's triangle. Can you tell me the numbers in the second row? The numbers in the second row are the same as the coefficients in the expansion with index 2. Now let's try it out with another expansion. Let's consider a plus b the whole cubed. And we know its formula, right? Yes, it's a cubed plus 3a squared b plus 3ab squared plus b cubed. What are the coefficients here? They are 1, 3, 3 and 1. Are the numbers the same as that of the third row of the Pascal's triangle? Oh yes, they are. So, what can we conclude from this? We can say that each row in a Pascal's triangle gives us the binomial coefficients for the expansion having any index.
Actually, there is one more point. See, this is Pascal's triangle. Now, this 6 is 3 plus 3, right? But this corresponds to this property in combination. NCR plus NCR minus 1 is n plus 1 CR. You can check this. See, this is 3C2 plus 3C1 as per property. It is 4C2. Yes, this is 4C0, this is 4C1, this is 4C2, right? So NCR plus NCR minus 1 is N plus 1 CR. See, in exam, if only one expansion is asked, then you need not construct this Pascal's triangle, but you should know what Pascal's triangle is. That is why we discuss this. So that's it for today.